Hello, everyone, and welcome. Today, we're going to understand a very fundamental concept in organic chemistry, the classification of haloalkanes. Now, it might sound very simple, but believe me, if you master this one idea, predicting reactions in your exams will become so much easier.
Okay, let's start with a small puzzle to get our brains working. Now, you would naturally think that a molecule which is very crowded, physically blocked, would always react slower, isn't it? But what if I told you that sometimes a very crowded haloalkane can actually react much, much faster than one that's completely open? How is that even possible?
Well, the answer to that little puzzle and actually many other questions in this chapter all comes down to one simple but very powerful idea: classification. If you understand this properly, you can predict exactly how a molecule is going to behave. So what is this simple rule? Let's break it down. Getting this right is the absolute key to predicting reaction pathways, which is so important for your exams, and also for understanding how we can build different molecules in a laboratory.
Fundamentally, classification is just a method of organizing. We are simply looking at the carbon atom that is holding onto the halogen. And then we just count how many other carbon atoms are its direct neighbors. That's it. That is the whole idea. First up, we have the primary haloalkane, which we write as 1 degree. Here, the halogen atom is attached to a carbon that is connected to only one other carbon. You can just imagine this carbon is sitting at the very end of a chain. It's very open, very easy to reach. Next is the secondary or 2 degree haloalkane. In this case, the halogen is bonded to a carbon atom that is connected to 2 other carbons. This carbon is usually found somewhere in the middle of a carbon chain, so it's a bit more crowded. And finally, we have the tertiary or 3 degree haloalkane. Here, the halogen is on a carbon that is bonded to 3 other carbons. So this carbon is at a branching point, making it very crowded. In chemistry, we have a term for this. We call it sterically hindered, which is just a fancy way of saying it is physically blocked by other atoms. Now, this is very important because it highlights a very common mistake. Many students just assume that all bromoalkanes, for example, will react in the same way, but that is not at all true. The most important point to remember is that the type of carbon, whether it is primary, secondary, or tertiary, is what really decides which reaction pathway will be followed. To make this idea really stick in your mind, let's use a very simple, everyday analogy. Just imagine a delivery service. This will make the idea of molecular crowding very, very easy to remember. Okay, think of a primary haloalkane like a package that's been left at a standalone house on a quiet street. The delivery person can just walk right up to it, no problem. A secondary haloalkane is like a package at a townhouse, which is in a row with other houses. There are neighbors on both sides, so it's a little bit harder to get to. And a tertiary haloalkane? That is like a package inside a central apartment complex, surrounded by high walls and gates. It's very, very difficult for the delivery person to reach it. So to connect this analogy to the chemistry, the delivery location is our haloalkane type: primary, secondary, or tertiary. The package itself is the halogen atom that we want to replace. The delivery person is the attacking chemical, which we call a nucleophile. And the ease of delivery is what chemists call steric accessibility. Basically, how easy is it to physically get to the reaction site? Now let's try another way to see this. Let's build a clear mental picture of what this crowding actually looks like at the molecular level. I want you to imagine a carbon atom, but picture it as a person sitting at a table. And this person has 4 arms, which represent the 4 bonds that carbon always makes. So a primary carbon is like this person sitting at the very end of a long bench. The side holding the halogen is completely open to the room. A secondary carbon is like a person sitting in the middle of the bench, with 2 other bulky carbon groups on either side, blocking the way. And a tertiary carbon? That person is completely surrounded by 3 other bulky groups. The poor halogen is trapped inside a circle of atoms. And this picture perfectly explains the simple rule for one type of reaction, called the SN2 reaction. In an SN2 reaction, a new group comes in and kicks out the halogen in one single direct step. So the more carbons that are attached to our central carbon, the less accessible it is, and therefore the slower this direct replacement reaction will be. The path is simply blocked. So you might be asking, why did chemists even create this system? Why does it matter so much? Well, it all comes down to one thing: predictive power. And this is the main point. Classification is the most powerful tool we have to predict how haloalkanes will react. By just looking at the structure on paper and identifying it as primary, secondary, or tertiary, we can make a very accurate guess about its chemical behavior without doing a single experiment in the lab. It's a fantastic shortcut.
Okay, let's come back to our opening puzzle. If a tertiary haloalkane is so crowded and so blocked, how on earth can it react faster than a wide-open primary one?
So, you might think that because it's crowded, it should just be less reactive overall. But here's the twist. Tertiary haloalkanes are very slow for one reaction type, the SN2, but they are extremely fast for another type, the SN1. You see, in an SN1 reaction, the halogen leaves first, all by itself. This creates a highly reactive intermediate called a carbocation, and the crowding from the other carbon groups actually helps to stabilize this carbocation, which makes it easier for the halogen to leave in the first place. So this is the big idea, the main takeaway. Classification doesn't just tell you if a molecule is reactive or unreactive. It tells you which pathway, which mechanism it's going to prefer. Primary haloalkanes prefer the direct one-step SN2 path, while the crowded tertiary ones prefer the two-step SN1 path. All right, let's do a very quick recap of the most important points from this explainer so you have them locked in for your exams.
First, the core idea is simple. Classification is just counting carbon neighbors, 1, 2, or 3. Second, always keep that mental image of the delivery service. Is the halogen at an open house or a crowded apartment? This tells you about its accessibility. And third, remember why it all matters. This is your best and most reliable tool to predict if a reaction will follow the SN1 or the SN2 mechanism.
And that is really it. If you can just remember that one simple core idea, hold on to one mental picture like the delivery service, and understand that key example of why a tertiary haloalkane can sometimes be faster, this whole topic will feel much, much lighter and easier to handle in your exams. Thank you for listening.